Okay, today we are going to continue the Gram-Schmidt process. Okay, so in the last lecture, we started the Gram-Schmidt process, right? So before starting, there were two kinds of concept: orthogonal projection and complement, right? So what was that? So with the subspace W and the given arbitrary vector y outside the subspace, then what I want to do is to to decompose this arbitrary vector y into the y hat, which is the orthogonal projection of the y onto the W space, and vector z, which is the component of the y orthogonal to subspace W, right? So as you can see this figure, the y hat will be the here, right? So orthogonal projection of the y onto W here. So this y hat vector and y minus y hat vector should be orthogonal each other. So in this case, z is defined something like this. So that is y minus y hat here, right? So this is the concept of the orthogonal projection and also orthogonal projection and component, right? So today we will introduce the QR decomposition method. Then we will, to derive the Qr decomposition factorization, we will use this kind of the concept such as the orthogonal projection or complement. And what was the Gram-Schmidt process? The Gram-Schmidt process is the way to produce the orthogonal or orthonormal basis for any non-zero subspace of Rn space, right? So I suggest you to compare the QR decomposition method, which will be discussed today, with the LU decomposition method. Okay, and what was that? So before starting, let's see the example. So when we have the subspace W, which is span of the x1 and x2, where x1 is something like this and x2 is something like this, and the question is to construct the orthogonal basis v1 and v2, right? So to find the orthogonal basis, we follow the steps something like this. So first of all, we want to start from the x1 itself. So let's say v1 is equal to x1, so v1 will be the starting point, and then we want to find out the v2, which is the component of x2 orthogonal to x1. So as you can see here, okay, here is x1, here is x2. What I want to do is to find out the orthogonal projection P onto the space W spanned by v1 or x1, and then find out v2, which is defined by x2 minus p, right? So what is the p? P can be represent something like this, right? So this is the formulation of the orthogonal projection of x2 onto the x1 space by x1, right? So the something like this, right? We already know the x1 and x2, so we can easily compute this term, right? And this term, right? So x2 is here. This is the constant value, and this is x1. Finally, v1 is something like this, right? So in this case, v1 and v2 should be orthogonal each other, right? Because the v1 is defined by x2 minus p, right? So and then v1 and v2 orthogonal each other. So v1 and v2 is an orthogonal basis for the W space. Okay, so this is the way to find out the orthogonal basis, right? Then we can extend this kind of the technique to the more of the three-dimensional space, or in this case four-dimensional space with the three basis vector, right? So what can we do? First of all, we already know the x1, x2, and x3 is clearly linear independent. Thus, it is the basis for the subspace W of R for space. Then the question is to construct the orthogonal basis for the W. So this is the goal of the Gram-Schmidt process, right? So what can we do? So we can follow the similar steps. The first one, let's start from the V1 and define the W1 space, which is span of the X1 or the V1. Then let's find the V2, which is the vector produced by subtracting from X2 each projection onto the subspace W1, right? So if you remember this figure, you can easily understand what I want to do. Okay, so and then V2 is equal to X2 minus projection of V1 onto the W1 space, right? Then you can easily compute these two values, and V2 will be something like this, right? In here, V2 is the component of the X2 orthogonal to X1 or the W1, and V1 and V2 is the orthogonal basis for the subspace W spanned by X2 and X1 and X2, right? And what next? We have to find out the V3, which is orthogonal to the W2 space, right? Then how can you do? Before that, we can scale the V2 to simplify the later computation because there is the denominator here, so we can scale this original V2 here, right? So to find out the V3, we can find out the projection of the X3 to W2 space, right? Because W2 space has the two basis vector V1 and V2. Then to find out this one, we can easily compute something like this here, right? So finally, V3 is the component of the X3 orthogonal to W2. That is the compute something like this. So V3 is finally here, right? Okay. So this is the illustration of finding the V3 by using the X3 and projection of the X3 onto the W space, right? And in here, V1 and V2 and V3 are orthogonal each other, right? So it will be the orthogonal basis for the W space, right? So yeah, so here you can see here finally V1, V2, and V3 is an orthogonal basis for the double space. Okay, so this is the Gram-Schmidt process. Okay, so if we described what we have done so far in a systemical way, the Gram-Schmidt process is formulated as follows. So given a basis of the x1 through the xp for the non-under subspace W of the Rn space, we can define the Gram-Schmidt process here. So V1 is equal to x1 and V2 is equal to x2 minus this one times V1, right? Actually, this is the orthogonal projection of x2 to the subspace W1, right? By V1, right? And what is the V3? V3 can be computed by x3 minus orthogonal projection of x3 onto the W2 space, which is spanned by V1 and V2, right? So this is kind of the recursive process, right? We can extend this kind of concept until the V2, VP, right? So in this case, V1, V2, V3, and VP will be the orthogonal set for the subspace W, right? So V1 through the VP is an orthogonal basis for the W, right? So this is the Gram-Schmidt process. In addition, span V1 through the VP is equal to V1 through the VK is equal to span X1 through the XK for K is larger than 1 and less than P, right? in here we can say that the subspace spanned by vector v is exactly same as the subspace spanned by x, right? So because this is the because if you remember this figure, so the space spanned by the v x1 and x2 can be exactly the same as the subspace spanned by v1 and v2, right? So yeah, we can easily understand what does it mean. So actually there is the proof, but we will just keep this one because we can easily understand it from the previous example, right? So yeah, then what is the orthogonal basis? Actually, by using the Gram-Schmidt process here, we can generate the orthogonal set or the orthogonal basis, and then we already know the orthonormal basis means each vector should have the unit length, right? So by just normalizing each vector computed here, we can just get the orthonormal basis, right? So in other words, if we find out the orthogonal basis by using the Gram-Schmidt process, then we can easily compute the orthonormal basis by normalizing them, right? So yeah, okay. So today we will just start the Qr factorization. Actually, it's not complicating, but it is related to the Gram-Schmidt process. And after this lecture, we will have the two kinds of factorization technique, right? So first one is the LU decomposition, and second one is the QR factorization, right? Right. So before starting, first of all, why we need the LU decomposition method? If we have the AX equals B problem, by using the LU decomposition technique, we can accelerate the computation of the solving AX equals B, right? So let's think about what can we do by using the QR factorization or QR decomposition method. Okay, so here's the definition. The QR factorization is defined something like that. So if matrix A is a m by n matrix with a linearly independent column, this is very important, very important. So let's say there is a matrix A, the size of the matrix is m by n, and each column vectors linearly independent, right? Then matrix A can be factorized as the A is equal to QR. So in this case, matrix Q and R, and the Q is the m by m matrix, which is the same, which has the same size as the matrix A, right? And whose columns form also normal basis for the column space A. So these vectors, these column vectors are also normal basis for column vector, a column space, right? So in other words, how can we find out orthonormal basis? Actually, we can find out orthonormal basis by using the Gram-Schmidt process, right? So it means that we can find out the matrix Q by by using the Gram-Schmidt process on this matrix A, right? So actually this is the Qr factorization. Anyway, then the R vector matrix R is an n by n upper triangular inverter matrix. The size of this matrix is the n by n and n by n, and upper triangular matrix something like this, right? And then this matrix is invertible, and invertible matrix with a positive entry on each diagonal. Positive entry on each diagonal, right? It's very intuitive, right? So let's prove this one, and let's think about what property of the matrix Q and matrix R. Okay, so let's start. So actually it is just enough to show how we can construct the Q and R in a way specify this theorem. So here is how. So first of all, let's think about the way to construct the matrix Q. Matrix Q here. Also normal basis of the column space, right? So how can we find out that? Actually, we can just use the Gram-Schmidt process, right? So where can we start? So we want to find out also normal basis for the column space, right? So first of all, we have to know the basis for this column space A, right? So we have to know the column space A. Interestingly, the columns of the matrix A form the basis of the column space A, right? Because this is the definition of the column space, right? Then let's say these columns be the x1 through the xn. So in this case, let's say matrix A consists of the x1, x2 through xn here. Xn, right? And then we can construct the also normal basis u1 and u1 through the un, right? Here for the column space A by using the Gram-Schmidt process, right? So we already discussed the Gram-Schmidt process in here, right? So we can just use this one to derive this basis. Okay, so by using this base, we can construct the matrix Q, which is defined something like this, right? In other words, by using the column vectors of the A, we can just derive the matrix Q, which consists of the also normal basis for the column space A. Okay, so let's do that. Okay, so this is just the construction of the Q. Actually, we can do this one in the next example, but here we can just to show that there exists the Q matrix, which is the orthogonal basis, right, of the column vectors of the A, right? Then let's think about the construction of the R. Here's the proof. So for k is equal to 1 through the n, xk is in span x1 through the x is k, right? x1 through the xk and u1 through the uk, right? Why? If you remember this one, it was the Gram-Schmidt process, right? It was the Gram-Schmidt process because the V1 through the VP is orthogonal basis for W, then we can just say that the span of the V1 through the VK is equal to span X1 through the XK, right? So we can use this property here, right? Then we can say that there exists the constant R1K through the RKK. So in other words, because this property, we represent XK with the V1, V2, and UK here with the some some constant value here, right? Then to make this formulation in a general way, we can just, actually there is no value here, right? But we can just think about there is the 0 times UK plus 1, 0 blah blah blah, and 0 times UN here, right? So make this representation as something like vector let's say U1 through the UN by RK, right? So in this case, RK is a vector consisting of here R1K through the R1K, okay, R1K through the RKK, which were the constant values to make a linear combination of the U1 through the UK to produce the XK, right? Okay, so we can find out this formulation, right? Then we can always make the RKK is larger than 0 or equal to 0. Why? Because if the RKK is less than 0, we can just multiply the both RKK and UK by -1, right? What does it mean? Because the UK is just the orthonormal basis, the one of the orthonormal basis. So UK and minus UK can have the similar property that fill the orthonormal set, right? So if you see this one, actually just think about this. V1 and U1 is same because the difference between V1 and U1 is just the normalization term, right? So let's suppose the V1 and V and U are same, and here if we replace the V1 as a minus V1, you will have the same sign of the value, and it makes some negative different sign value, and this term also makes the different sign value. It means that by multiplying this, there is no sign change here. So it means that if we just negative orthonormal basis, those remaining bases are not changed, right? So we can easily think about multiply both RKK and UK by -1. We can always make the RKK larger than 0 or the equal to 0, right? And using this linear combination representation, we can construct RK here, RK, which is the kth column of the R, something like this, right? Something like this, right? So in other words, so R1 should be non-zero value here, but zero everyone. R2 should be like this. RK K 0 0, right? So this is the definition of RK. Then we show that there exists some constant values here, right? To define R matrix vector R, right? And then we know the xk is equal to vector q times rk, something like this, right? Because this is a q matrix q, right? Here, right? So xk is the q times rk. Okay, q times rk for k is equal to 1 through the n, right? Then let's say the matrix R is equal to R1 through the Rn, right? Then, okay, now we can represent the matrix A as a Q times R1 here, Q times R2, and Q times Rn, then which will be represented by Q times R, right? So here, R is here. So the fact that the R is invertible follows so easily from the fact that the columns of the matrix A are linearly independent. So actually to prove this one, we need some kinds of knowledge, but I can just show you some very intuitive proof. So let's say there is the vector that satisfies Rx is equal to 0. Then by multiplying Q on left hand side and right hand side, QR X is equal to 0, right? So in this case, QR is equal to A, so it means A is equal to 0, right? A is equal to 0. Then the columns of the matrix A are linearly independent, right? Because it was the assumption, right? Then X must be 0, right? Because the matrix A are linearly independent, right? So it means that there are only trivial solution as X is equal to 0, right? Then in other words, if we think about here, Rx equal to 0 has only trivial solution, so it means that matrix R, the columns of the matrix R is the let's say columns of R linearly independent, right? Linearly independent, and matrix R is the square matrix. Then we can say that it is the invertible by the invertible matrix theorem. Okay. So by using this one, we can say that the matrix R is the invertible matrix. Okay. Then since R is a clearly upper triangular, right? Because here something like this. So if we transpose this one here, then we can clearly show that this is the upper triangular, and we already know that this is the invertible matrix. Then so the diagonal entry RKK, diagonal entry here, RKK should be non-zero. Okay, so non-zero. Okay, so it means that by combining this with the fact that RK is the larger than 0 or the equal to 0, then RK case must be the positive value. Positive, because the non-zero and larger than 0 make the positive one. Okay, so this is the proof of the QR factorization. to summarize, by using the what's that, Gram-Schmidt process, we can generate the matrix Q, and according to the matrix Q, we can define the matrix R. Then my matrix R has some kinds of properties, such as it is the upper triangular undertone matrix with a positive entry on each diagonal, right? So this is the QR factorization. Okay, so let's see the example. The question is to find out the QR factorization of the matrix A, where the matrix A is defined something like this, right? So let's do that. So first of all, let matrix A is the three vector x1, x2, and x3. We first obtain v1 is equal to x1. So this is the step one of the Gram-Schmidt process, right? Then because we want to find out the also normal basis, then we start with the normalized vector u1 from the v1, right? So in other words, u1 is equal to v1 over length of the v1, right? Then first of all, because the x1 is equal to v1, so it means that yeah, let's say it like this: v1 is equal to length of the v1 times u1, right? Then actually in here v1 is equal to x1, so we can compute this one, right? So in other words, yeah, x1 is the length of the v1 u1, so it means that this is the this is the length of the x1, right? Because the length of the x1 is equal to length of the v1, right? So in this case, r11 is equal to 2, so vector r is the 2, 0, 0. Okay, so this is the first step. In the second step, in Gram-Schmidt process, we can find out the v1, right? So v1 is equal to x2 minus projection of the x2 onto the w1 space spanned by here v1 or u1. Okay, in this case, let's think about the space spanned by u1, because we want to find out the orthonormal basis set. So what do we want to do? So x2 minus x2 inner product u1 over u1 inner product u1 times u1. So it should be u1. Okay, so u1 is here, x1 and x2 is here, so we can easily compute the x2 minus 3 over 2 with the u1 here, right? So it'll be the negative 3 over 4, 1 over 4, 1 over 4, 1 over 4, right? Then actually this is the v2, but we want to find out the normalized unit vector, or the normalized vector u2, because we want to find out also normal basis, right? So the u1 is computed something like this, right? So in other words, the u1, this is actually v1, v2, right? So u2 is the length of the v2 and v2, right? Then we want to represent x2 in terms of the u1 and u2, right? So from this one, we can represent x2. Oh, x2 is equal to v2 plus u1 u1 x2 u1 u1, right? So we can represent v here, v2 is equal to length of v2 and u2, right? So by substitute this one here, then we can easily compute this term and this term, right? So you can derive this one yourself, but it is also very easy to understand. But so we can represent x2 as in terms of the u1 and u2. So here this is r2, right? r2 is equal to it's not a what's that? R2 is equal to plus 3 over 2 plus 3 over scale 12, right? So yeah, it was the x2. Actually, this upper part is really easy because this is the same process of the Gram-Schmidt process, and this part is also easy, but the difficult parts are here and here to find out the vector r, right? Actually, it's not a efficient way to find out vector r. In the last page of this lecture, we will derive the more efficient way to find out the matrix r without doing such a really complicating procedure. So you don't need to worry about this. This is just a way to show the how can we compute the matrix R. Okay, so let's just try to understand what does it mean. So finally, in step 3, we can generate the V3 as x3 minus projection of x3 onto the W2 space spanned by u1 and u2, right? And so this is u1 and u2, right? So the computation is really intuitive. So here we need to compute this one, right? So we already know the x3 and the value here. This is u1. So there should be some kind of constant with the u2 because u2 is here, right? So it might be just 1, right? So by using this one, we can generate the V3 here, right? Then we want to get the vector u3 with a unit length. So u1 is something like this, right? So in this case, it should be normalized. So yeah, find out yeah. So it should be -6. So today there are some typo errors, so please try to fix this with your pen, right? So this is a U3, right? So from here you can also represent the vector x3 in terms of the u1, u2, u3, right? So actually you can compute this value by using the fact that v is the length of the v times u. So you can just compute this one. So the result is something like this, right? So in other words, R3 is the 1, 2 over scale 12 and 2 over scale 6, right? So square root 6, right? So this is R3, right? Okay, now we have the matrix Q consisting of the U1, U2, and U3, and we have the matrix R consisting of the R1 and R2 and then R3, right? So So from the matrix A, we factorize the matrix A onto the Q matrix U1, U2, and U3, and R matrix, something like R1, R2, and S3. Okay. So this is the factorization, right? QR factorization. So we can generate or decompose matrix A onto Q and R. Okay. So this is the QR factorization. Actually, if you just follow these 3 pages, actually it looks really complicating to find the matrix R because it needs the more complex way to estimate each vector R. So we will think about the more efficient way to compute this one. Okay, so from A is equal to QR, so what do you want to do is just want to find out the matrix vector R, right? So we can multiply the Q transpose on left hand side and right hand side. So it will be Q transpose A is equal to Q transpose Q R, right? So question, what is the Q transpose times Q? What is that? When Q consisting of the also normal vectors in column space, in each column. What was that? Identity matrix, right? Because if you go back to the our lecture when we introduced the also normal vector, there was the definition that Q transpose Q is equal to identity matrix, right? So if you don't understand this one, just derive the matrix Q as a U1 and U2 and U3 and just transpose U1 and U2 and U3 and compute this one, which makes some identity matrix, right? So finally, it means that here's just R, so R can be computed by Q transpose A, right? It is very good indicator. So we already know the matrix A, right? Then we can easily find out the matrix Q by using the Gram-Schmidt process. Then by multiplying transpose Q to the matrix A, we can find out the matrix R, right? So in other words, in the previous slide, we derived the matrix Q, so it consisting of the three vectors, vector 1, vector u1, u2, and u3, u1, u2, and u3, and by transposing this, we make some this vector, this matrix, and this is A, right? Then original A is here, right? So by computing the matrix multiplication between this Q transpose and A, we can easily compute the each value, right? How can we do that? By computing this, we can compute this one and this one, right? For computing this, we can easily compute this one and this one, something like this, right? Anyway, we can easily find out the matrix R here, right? So it is much easier than those kinds of the way to find out matrix R, right? So to summarize, if we have the back matrix A, we can decompose as the matrix Q and matrix R, and matrix Q consists of the also normal basis also normal basis for the column space of the matrix A, and matrix R is the upper triangular matrix, which is the inverter matrix, right? With the non-zero, with the positive values in each diagonal, right? So this is the QR factorization method. So actually, this QR factorization method will be used in the next week's lecture in the least square solution, and which will be also used in the eigenvalue decomposition, or the some kinds of the technique in singular value decomposition. Anyway, so there are a lot of the way to be used in the linear algebra thing. So actually we almost done, but here are some remaining techniques such as eigenvalue decomposition and singular value decomposition, right? So after studying those kinds of technique, now we will have some kind of we will kind of the way to understand any linear system that can be represented by the ax equals b or the ax equals 0, right? So after learning the remaining part of thing, let's summarize what we have done so far, and then let's finish this semester's course. Okay,